Okay, this is the material for our course introductions. Firstly, as usual, we need to give you some idea about what it is. We are structure 2, make sure that you come to the right class. And some background about this module. This module is QF level 5. And suppose before taking this module, you should have passed the other module called Theory of Structure 1, which is a fundamental structure analysis module. In Theory of Structure 1, you have learned something like how to solve indeterminate structures, how to use so-called slope diffraction equation, moment distribution method, etc. Those classical methods has been presented in Theory of Structure 1. At least you know how to plot moment and shear force diagram, I think. And then these are my informations. If you want to, if you have questions regarding to the course material, you may send me email or you may call me. The module aims. The aims of this module is to equip students some understanding of complex structure analysis theory, and those theory are useful for you to solve some structural problems for both determinant and indeterminate structures. We will discuss so-called Stibbs method. One very universal and general approach help you to solve almost all kinds of structural problems. Although the calculations is a little bit complicated, but it's very, very general. And also help students to develop their problem-solving skill to solve some engineering problems. We will also discuss the other advanced knowledge like structural dynamics and also plastic theory. You will see their names later. And then we have some workshops to introduce computer software for computer analysis or structure analysis. When we set up our modules, all modules, basically we need to firstly define our module learning outcomes. In this module, we have totally 4 learning outcomes. They are the they are the things that suppose you need to achieve when you finish this module, and when you get a pass grade, suppose you need to fulfill all the outcomes. Firstly, you have to learn what is Stibbs method, and then you need to know something about plastic theory, upper bound theorem, lower bound theorem. There are some classical theory in plastic theory. And finally, you have to know something about structural dynamics. Not very deep, but at least you have to know what is structural dynamics. You have to learn so-called degrees of freedom, modal analysis, time history analysis, etc. Throughout this module, we will discuss each concept in detail, step by step. And then we need to learn some computer software. In this module, we will discuss SAP 2000. And the next time in your next semester, we will discuss another one called ETABS. They are a very common software for structure analysis in the industry in Hong Kong. SAP 2000 ETABS. Actually, they're developed in the same company. They changed the platform a little bit. SAP 2000 is more general software, while ETABS is mainly for tall buildings. Some background about this course information. We have lectures, we have tutorial, we group them into 3 hours on Friday morning. And we have workshop, we have lab. The lab, suppose we will conduct in our campus at the 10th floor, room 1012. And the computer lab is just next to the lab venues, room 1011, computer lab. The lab we will discuss later. I will send you the lab menu very soon. For the lab, you have to form group. Each group of students composed of around 5 to 6 students normally. And then they need to do a very simple test to measure the reaction, measure the only reaction, yes. And then you can use some theory to verify your lab result. This is how you can check your theory. Once you have a theory, you have to verify the accuracy. How to verify? Do experiments. And then we will discuss computer software. This is some introduction about the lab. We will have another more detailed discussion later. This one is just for your briefing. The lab, you have to conduct a very simple 2-span beam test. This will be probably the setup. It's not very clear, so I try to draw the things clearly on the pictures. 2-span beam, span 1, span 2, two span. One end is fixed, and then you have two raw supports at the middle and at the right. You have to apply loadings. You apply two loadings on each span, and then suppose you can measure the reactions. You can record the reactions using the meters at the bottom. And this is what you have to do. Measure the reactions during the lab, and then use the theory to verify the results. So this test is first relatively short and simple to check the accuracy of Sipper's method, matrix approach. About the workshop, in the workshop you will learn SAP 2000. Maybe some of you has already learned how to use it. It's a very general software for structure analysis, not only for building. You can also use it for the other structures like shell structures, truss bridge, many things. Very, very general. SAP 2000. I think this workshop is scheduled on Thursday evening. When you check your calendar, the timetable, you should see two sections get scheduled on Thursday evening. Actually, they are the SAP 2000 workshops. Quite useful. You can find out the diffraction, you can find out moment, reaction, shear force rapidly if you know how to set up the models. When you use your hand calculations, I think you can't handle a very complicated structures like this. This one is not very complicated, but if I ask you to use hand calculation to find out the reaction, it's not easy, right? But if you use computer software, I believe that you can find out the result within 15 minutes. Apply loadings on the structures, and then you can measure the diffraction. Model analysis, we will also discuss model analysis. Model analysis is, you can call it dynamic analysis to find out some dynamic properties, especially the mode shape and the modal frequencies or modal periods. There are some useful indicators to describe the dynamic properties of the structures. You will know what they later. Some textbooks call this argument analysis, but normally we call this mode analysis. Now, this perhaps the most important things in these introduction materials. How we assess your final grades? Well, we have two items. Item 1, continuous assessment. These are the things that we keep assessing you during the semester. We call it continuous assessment, CA. The contribution of CA is 50%. CA composed of 3 sub-items. Item 1, midterms. Midterm test. The midterm quiz, maybe I can call this quiz only, because it may not happen at the middle. Middle means week 7, week 8. But depends on our progress, depends on the other setting. Maybe the quiz will be maybe not at the middle. So I think it's more probably called this quiz rather than midterms. But basically the quiz cover topic 1 to topic 5, and the contribution is 30%, the quiz. Topic 1 to topic 5 mainly talk about all the things in Sipper's method. And then we will also assess you a little bit about structural dynamics, a little bit, not very deep. This is about the quiz, mainly Sipper's method, 30%. And then we have 2 assignments, homeworks. We have 2 homeworks, and the first one is for Sipper's method, the other one is for structural dynamics, the simple one. The total percentage is 10%, and then because we have lab, we have workshop. So according to this setting, we have to also give you some assessment items for the workshop, for the lab, 10%. So totally, we have 4 things. You have 4 things to be submitted: 2 homeworks, 1 lab report, 1 workshop report. Maybe I can call this workshop report or workshop exercise. 4 things, and then the remaining 50% becomes the final examination. Suppose in December you need to join our final examinations, 50%, 50-50. This is the grade distribution of this module. So please make sure that you understand this table. This informations. You have to understand how we give you marks. Try to submit all the assessment items as much as you can. so that I can help you to pass the module. Otherwise, if you miss something, it's quite difficult for me to, do some adjustment. But anyway, yeah, this is how we give you marks. So I think you have some basic idea about what the arrangement of this module. In this module, you know the learning outcomes, you know the objectives, right? You know the assessment items, and you have some idea about what we are going to do. We have lecture, we have tutorial, we have workshop, we have lab, we have everything. Then what next? Some discussion about the contents. Actually, in this module, we have three main chapters, three big chapters, three big things we were going to discuss. The first one is Stipless method. Stipless method is a very classical analysis method to handle truss, beam, and frame structures. Using Stipless method, you can handle almost all kinds of situations. There are three subtopics under this chapter. Topic 1, that means today, we will discuss trust. Trust perhaps is the most simplest elements we can start with. And then maybe next week, I think next week we are still talking about topic 1. In week 3, suppose we can move on to topic 2, beam element. Similar concept, but we change our target to. And then finally, sorry, there's a message. Yes, but I can't see the student right now. I think he's already joined our class, right? If some student in the waiting room, please help me to click the accept item. During the present mode, I can't click the things easily. Let me continue my discussions. I forget what I just mentioned. Anyway, the first part is about Stipless method. And then I think starting from week 4 to week 5, we can start to discuss another big topic. Starting from, I think, week 5 normally, we can move on to another big topic called structural dynamics. Normally in the past, when you learn structural analysis, we're talking about static problem. Static problem means something that does not move. They just stand there. They may under some deformation, but they will not move. But in structural dynamics, you can see the structures start to oscillate, start to vibrate. At the beginning, we will discuss SDOF. You can take a look of this term at this moment. You don't know what it is. We will discuss what are they later. They are so-called single degree of freedom system, SDOF, single degree of freedom. And then multiple degree of freedom system, MDOF. There are two very classical systems we are going to discuss in structural dynamics. Almost all the textbooks using this terminology, SDOF, MDOF. They are so-called single degree of freedom, multiple degree of freedom systems. You will learn how to handle a structure under dynamic loadings in chapter 2. And then chapter 3, plastic theory. Plastic theory normally is a relatively short and simple. It's normally take around, I think, 2 weeks to complete plastic theory. Relatively simple chapter. We start to talk about the behavior of structural elements after yielding. In the past, we normally consider elastic, but in plastic theory, you need to focus on the yielding behavior. So these are the 3 main chapters in this module: Stipless method, dynamics, and plastic theory. Our quiz mainly focus on Stipless method. The quiz mainly focus on Stipless method, and we will also assess a little bit about structural dynamics in the quiz. Right. Topic 1 to topic 5, if you still remember the content, the range of the quiz. Oh. The final examination. Well, as expected, final examination will cover all the contents for the final examinations. About the arrangement of the quiz. At this moment, we expect to have a face-to-face quiz. So students need to come back to the campus to join the quiz in face-to-face mode. At this moment, this is the arrangement. for the quiz. For lectures, for tutorial, you can join using MS Teams, doesn't matter. But for the quiz, you have to come back to join the quiz. Okay, quiz face-to-face. Normally, the quiz normally arranged in week 9 to week 10. Week 9 to week 10. Quiz. I think it's around week 9 to week 10. Depends on our progress. After introducing all the contents, I need to give the assignment and give you the solution. So suppose week 9 to week 10 is appropriate. Lab report. The lab section, I forget the timetable. Do you have the timetable? Yeah. I don't have the timetable at this moment. The lab report. Normally, I allow students to submit lab report and workshop report before the end of this semester, normally, which means you can submit before week 14. Yeah, relatively flexible. Final examination, we will send you the exam schedule later. I think at the middle of the semester, you will receive the exam schedule through email. The mode of final exam, I'm not really sure at this moment. I think maybe face-to-face, just like the quiz. But you know, the pandemic situation is changing every day recently. So keep tracing the email. We will update you once we have some advanced announcements. Yes. Finally, some reference books. If you like to read books, then there are some suggested textbooks you may be referring to. For this module, I think it's quite difficult to buy a single textbook because you can see that we have totally 3 different topics. There are 3 different topics. Normally, they appear in 3 different textbooks. So it's quite difficult to buy a single textbook to cover everything. But I think in the past, you have maybe you have already purchased a textbook for structure analysis. Actually, this is the textbook for theory of structure 1, our previous structure analysis module. You can also use the previous textbook. I believe that most of you have some textbook for structure analysis. When you go to the last few chapters, basically they are talking about Sipper's method. At the beginning, they talk those fundamental concepts called discuss the energy principle, virtual rate principle, Stokes diffraction equation. But in the last few chapters, they start to discuss Sipper's method. So I believe that you can use your previous textbook to get more information about Sipper's method. For structural dynamics, maybe you do not have textbook for structural dynamics. Here I give you one reference. This is Dynamic of Structures, quite lengthy. This textbook written by A.K. Chopra is very famous researchers in the field of structural dynamics and earthquake engineering. A very fundamental textbook for structural dynamics. We will discuss some contents in this textbook. Not all. We don't have enough time to cover everything. And also the other reference books if you like. But I believe that the course material should be sufficient. I will also give you some examples for each chapters, so don't worry about the examples. So these are all the things. These are all the things about our course introductions. Okay. Is anything you want to ask me? The assessment method, the lab, or the other thing else? Yes. Maybe the first part, I think. Have you learned anything about matrix algebra? Yes. And then do you know how to plot moment diagram and shear force diagram? Then you have to refresh your memory. Okay. Yes, they are more related to the first chapter, Sipper's method. For structural dynamics, I believe that structural dynamics are new to everyone. Same for plastic theory. No further questions. Then I will move on to another PowerPoint. Yeah, also some background information about this module to tell you what you need to learn before these modules. Suppose you have passed the other structure analysis module. And let me share the screen with you. This is the introduction material, let you know the background, what you have to learn before studying the first chapter. You should have some fundamental knowledge first. As we've spoken in the previous PowerPoint, you has already passed the other theory of structure 1. Then what you have learned in theory of structure 1? Basically, theory of structure 1 is a fundamental structure analysis module. In this module, you have learned how to analyze the performance of a structures. A structures can be a frame, can be a beam, can be a truss, can be any other kind of structures. To determine their response. What I mean response? Normally, response means two things: internal forces, moment, shear force. We have a lot of practice to let you practice how to draw shear force and moment diagram in the past. In year 1, you have a module called structure mechanics and mechanics materials. We start to introduce how to plot moment and shear force diagram. In year 2, you have studied theory of structure 1, which is also emphasized on this concept, moment and shear force diagram. Right now in year 3, again, moment and shear force diagram again. These are very, very important concepts for engineering applications. So normally when students do some interview in consulting companies, normally the engineers would like to ask them to draw moment and shear force diagram as some interview questions. So please make sure that you know how to play with this drawing. Yes, it determines structural response, firstly about moment and shear force, and the other thing is about deformations. How many millimeters moving downward or upward, right? Deformations of members, structures. The purpose is to assess the safety issue. Right? We don't want structure broken. We don't want structures to have too large diffractions. So you have to firstly check the results, check the performance by doing structure analysis. And the other purpose is for design. Without knowing without knowing moment and shear force, you can't do your design, right? When you do your steel beam design, what you need to know? Steel beam design, normally you can start from the moment equation, right? What about steel beam? For steel beam, the moment capacity is equal to the design strength times plastic modulus. So if you know moment, if you know the design strength, then you can go to section table to find out the appropriate plastic modulus. Why I ask you steel? Because I taught students steel design in year 2. Anyway, it doesn't matter. This is analysis module. I will not ask you too much about structural design. Don't worry. This is the reasons why you need to know structural analysis. Without knowing these skills, you cannot assess safety. You cannot design members. Then how to conduct a normal structure analysis? Firstly, structure idealization. Given you a structures, you cannot firstly do the analysis directly. You have to make some assumptions, idealizations before working on the problems. We call that structure idealizations. And then input those basic informations, say, for example, the physical properties, the height, the width. You have to also input the loadings, right? Without this information, you can't do the analysis. These are some basic things. And then after that, you can do calculations to firstly calculate the reaction as a suppose, and then you can use the result to calculate the other internal forces like moment, shear force, axial force, depends on the nature of your buildings. And then you can calculate the other structural response further, diffraction or the other thing else. These are the normal procedures to conduct structure analysis. Define the problems, basically, define the problems, and then do calculations. This is the previous module, theory of structure 1. This flow chart shows you the most commonly used method of analysis for structure analysis. We start from here. If you want to do a structure analysis, firstly, you have to classify the structures. We have two kinds of structures: statically determinant structures, statically indeterminate structures. Two things. What are the difference? Determinant, indeterminate. Determinant means you can find out all the reaction directly using equilibrium equations. If you can find out all the results using equilibrium equations, that means it is determinant structures. Determinant structures. The number of unknown reactions equal to the number of equations. Determinants. Then what about indeterminate structures? Indeterminate structures mean you cannot find out the reactions simply using equilibrium. You need more equations. You need more equations. This is indeterminate structures. And then in theory of structure 1, the fundamental analysis module, we start from here, determinant structures. And then you have learned how to find out the force using equilibrium equations. You have learned how to find out the displacement using a set of methods. At the beginning, you have learned how to use double integrations to find out the fraction of beam. Hello? I hope you still remember how to use integrations, although I think we seldom use it in practice, but there are some classical approach. Integrations. Moment area method. They are also helpful to find out the fractions of a beam, something like that. Conjugate beams, also the other approach. Energy method. You can use energy principle to find out displacement of structures. You have learned virtual work principle. You have learned Cartesian theorems. There are two classical energy approach to find out the fractions of charge of beam structures. And then we move on to the other topic, indeterminate structures, right? If there are two, if you need to find out the response of indeterminate structures, then what you can do? There are three methods you may use. The first one, force method. Force method based on superpositions. You use superpositions to decompose a complex problem to several simple problems and then solve it individually. Finally, superimpose them together, force method. This is the thing that you have already learned in theory of structure 1. They are not new, okay, not new. I just review a little bit what you have learned before. Displacement method. You have learned Stokes diffraction equation. You have learned moment distribution. Moment distribution take you a long time to do the calculation. You have to calculate the distribution factor, find out the fixed end moment, and then do many iterations. But doesn't matter, everything has already gone, right? You have already passed theory of structure 1, so you're expert in this area. Then what about this module? In this module, at the beginning, we focus on this part, this small part, Stippler's method. Stippler's method is also classified as a method to analyze indeterminate structures under the category of displacement methods. In this module, we go deeper into this approach, Stippler's method. Or you may call this matrix method. Finally, there is a list called approximate analysis. Approximate analysis, there are two common approximate analysis we have learned before, Portal frame method and cantilever method. They are used to assess the behavior of a rigid frame, frame structures, by putting a lot of assumptions. But anyway, I assume that you have learned these kind of things. So I just focus on Stippler's method at the beginning of this module. Okay, I just focus on this part. Normally, I will not ask you the previous concept. That means I will not ask you Stokes diffraction. I will not ask you moment distribution. Okay, but for your own good, try to review the contents. In this module, we focus on Stippler's method. Okay, given the structures, suppose we have a beam, we have a column. A beam is supported by, on one hand, is supported by another column. On the other end, is supported by another beam. This beam is a universal beam supporting a loading, a cloud. If you want to find out the response of these structures, then what you have to do? According to our previous flow chart, firstly, you have to convert a structures so that it becomes the one that able to analyze. We call that structure idealizations. You can replace the support of the left-hand side to a pin support. You can replace the support on the right-hand side to a roller support. And then you can replace a cloud, the loading, to maybe a concentrated force or maybe a distributed force, depends on the nature of the loading. You may have UDL, you may have point force, or the other thing else. We convert the support conditions to pin, to roller. We change the loading to concentrated force. Finally, it becomes what? It becomes a simply supported beam under point load, maybe at the midspan, right? You can find out the moment. You can find out the shear force immediately, suppose, right? What about the moment diagrams? If I ask you this question, you need to answer me immediately, right? Moment diagram, a straight line, right? What I mean is that this is so-called structural idealization. You have to convert the boundary condition, the loading, to something that you can handle. What kind of boundary conditions we have? What kind of support conditions we have? Normally, we have pin support, we have roller support, we have fixed end, right? We normally play with these three support conditions. For loading, we may have UDL, we may have point force or the other distributions. You can also use this concept for a 3D frame, a frame structures. You can simplify the loading, the member geometry, so that it becomes something that you can analyze. Say, for example, you can change the slab at one-way slab. One-way slab tell us what? One-way slab tell us the load distribution, right? For one-way slab means the loading go to the left or go to the right in the form of uniformly distributed load. This is the condition of one-way slab. One-way slab tells you the load distribution on the adjacent beams. We have one-way slab, we have two-way slab. We have learned how to design them before. I hope you still remember. RC one-way slab, RC two-way slab. And then you can simplify a beam column to a straight line. Then it becomes a very nice model for you to analyze. You can convert this to something like a 2D frame, support condition, pin end in this picture, right? You can see a triangle at the bottom. Triangle means it has a pin support and the UDL. If you have time, then maybe you can find out the moment diagram, shear force diagram for these two-story frame structures. Support conditions. As I mentioned before, we have basically three types of supports, but here I show you four. There is one special support you may encounter in these modules. Support. We have two examples right here, example 1 and example 2. Example 1 is a classical beam element. One end is pin support, one end is roller support. For roller support, we have two symbols to represent roller support. Sometimes I use simple a circle to represent roller support. This one is much more easy for me to draw. But when you read the textbook, sometimes they use this just like a car, right? Just like a car to represent roller support. They mean the same thing, roller support. Fixed support. Fixed support is represented by this triangle normally. Pin support. Pin roller. And what about the properties? How many reactions provided by pin support? Similarly, how many reactions provided by roller support? This question is simple, but you have to know it before learning Sibber's method, because this concept affects you how to set up the problems when you use Sibber's method. How many reactions at pin support? 2, right? Pin support, by the definition, pin support prevents all translational movements. That means the structure cannot move up, cannot move horizontally at this point. This is the definition of pin support. So in this sense, we should have some restraints to prevent the movement applied at this point. Restraint means we have reactions. We have horizontal reactions, we have vertical reactions to prevent this pawn move up, move down, move left, move right. Okay, we have two reactions at pin support. And we have one reaction at roller support. Roller support prevent this vertical movement. Right? The beam here cannot move into the ground, right? So we should have some restrictions to prevent the vertical movement. It represented by these vertical reactions. But roller support allow this pawn to move horizontally. Horizontal movement is allowable for roller support. So we have only one reactions at roller support. Two at the pin, one at roller. So the beam may probably deform in this manner if it is under a downward force P. At the same time, I list out the possible movement. At pin support prevents horizontal and vertical translational movements, allow rotation. You have to understand these things because when you use Sibber's method, you have to identify this property yourself. When you use Sibber's method later on, you have to identify which displacement is allowable, which is not allowable. I will not tell you the answer. When you use Sibber's method, you have to identify yourself. Prevented, if there is no horizontal and translational movement, that means the movement are zero, right? If allowed to rotate means it is unknown, something that you have to calculate. Same for roller support. Roller support allow two possible movements. Allow move horizontally for this setup. Allow the member rotate at this point. But roller support prevent vertical translational movements. I give you one remark on the right. The roller support depends on the orientation of the roller support. Sometimes we can have another orientation. The roller support can be on a vertical wall. So in this case, you have to change the definition a little bit. You have to read the picture carefully yourself. Example two, one end is fixed end, the other end is a so-called slider. Fixed end is a very strong support, which can give you three reactions, two forces and one resisting moments. Fixed end. Fixed end, on the other hand, does not allow the member to translate or rotate at this point. No movements, no rotation. That's why we call this fixed end, fixed support, a very, very strong support conditions. Then what about slider? Slider is not common, but some textbooks also use it in some examples. What about slider? Slider is quite special. It is not a roller support. Because when you take a look on the reactions, you can see that slider can provide you two reactions. One, force. The other one, resisting moment. This is the reactions provided by slider. When it displays, it's probably in this manner. You can see some vertical movement because slider allows the structure to move vertically, just like a car. But it does not allow the structure to rotate at the end. So at the end right here, you can probably see 90 degrees. The slope here is 90 degrees. No rotation is allowed at the slider support. Quite different from roller support. Please distinguish roller and slider. You can refer to this diagram later on. These are the support conditions we probably considered for 2D structures. Again, you have to understand how to identify the number of reactions and the movement properties, which prevent it. It will affect you how to solve the problems later. Or maybe you can go back to this page later on. The other things that you have learned is what is so-called the external force and internal force. I just copied the definition from the textbook. I put it here because I found that students normally confuse between external force and internal force. External force means something applied on the structures that you can see directly from the picture, just like here. Apply force, reactions, they apply that on the structures directly. So they are so-called external force. From this picture, you cannot see internal force. Right? Internal force means internal, something inside the structures. You cannot see it. You cannot see it directly. Okay. Then how to visualize internal force? Internal force mean moment, bending moment, shear force, axial force, that kind of things. How you can visualize internal force? If you want to find out internal force, you need to put down the free body diagrams, right? Say for example, you make a cut right here. If you want to know the internal force, you make a cut at your target sections. And then you can now see the internal force, right? We have shear, we have moment at this cut. They are so-called internal force, okay? Don't confuse, one is external, one is internal. If I ask you to find out internal force, which means I want you to find out moment, find out shear, these kind of things, okay? Don't confuse the properties. Because you can see that we have too many symbols on the texture, right? We have applied force, we have reaction, we have internal force. So please distinguish the difference between them. When you draw moment diagram, when you're asked to draw moment diagram and shear force diagram, moment shear force diagram are referring to internal force, not external. And some example about structures. We have truss. Truss perhaps is the most simplest kind of structures. Truss. When you see this term truss, truss means the members are only under axial force. It can be in tension, it can be in compressions, which means truss structures. One more conditions. When you see the term truss, truss means the joint are pin joint. All joints are pin joint. So that bending moment cannot develop along the members. Truss structures or are actually loaded members. Truss bridge is a classical example. And then we have a beam element. Beam element is mainly under bending, involving two actions, bending and shear. When you analyze a beam, you need to know the bending moment and shear force. Beam. Frame, maybe you can call this column. In steel design, we call this beam column, okay? Or you may call this frame member. Frame member is a very general member because it can use to capture axial force, bending moment, and shear force, which means that frame can use to analyze a more complex scenario. When a member under all kind of internal forces, then you need to use a frame member to model their behavior. Frame. In steel design, we call this beam column, but they mean the same things. In engineering practice, sometimes we use special elements like cable. You can see cable from cable stay bridge. This is Kapshemen Bridge in Hong Kong. You can see many cable. Cable is also a very special kind of elements which only take tension. They does not able to take compressions. Actually tension member cable used to support the bridge deck so that they will not deform too much downward. Another one is shell element. Shell element is totally different from the previous element, right? In the previous page, you can see that all elements are just like a line, just like a line. You can call this 1D element, a line element, 1D, they're straight line. But shell element is a plate, 2D element, or you may call this area element, just like a plate. How I use it? If you want to model a shell like this, then you need to use shell element. Or if you want to model shear wall is also a plate oriented vertically, right? Shear wall. If you want to model wall, then you also need to use this kind of area element. Normally, you can use area element. I'm not use always, normally, okay? But you can use the other method to do the modeling. Computer modeling is quite special. We have many modeling skills. For area element, there are 3 types of area element in general: plate, membrane, and shell. We have 3 types of area elements. We will discuss more during the workshop, SAP 2000 workshop. In our lectures, we will not put too much time on area element. We mainly focus on 1D element. Because every element is quite complicated, it's not able to analyze using hand calculations. Why? For an every element, you can see that we have many degrees of freedom. It can translate vertically, horizontally, or it can rotate. So you can see that you have many possible movements. It makes the calculation very complicated. Normally, if you want to analyze the shell structure's behavior, we need to rely on some computer software like Z2000. In this module, we basically focus on fundamental theory for truss, for beam, for frame. Once you know the theory, then you can extend a little bit to the other structural elements. 1D, 2D, then you can expect that in reality, we have also 3D element, right? 3D element. 3D element is just like a solid element. Okay. A beam, right? We talk about beam. A beam. The model is as a straight line, right? In this picture. But actually for a beam, maybe I use concrete beam. Concrete beam is much more easy to visualize. For a concrete beam, instead of modeling a concrete beam using a straight line, actually you can cut a concrete beam into many small quick. You can cut concrete beam into many small quick, and then you join these small quick together. It becomes a whole beam. This modeling is using 3D element, many 3D elements. So you can see that to analyze the performance of structures using computer modeling, you have more than one way, always more than one way to model our structures. You can model using a straight line, or you can model it using many small cube elements. But you can see that if you model using small cube elements, the computation, the calculation effort becomes much more higher. You need a more advanced computer in order to solve this problem. Why? Because if the model is a straight line, if the model beam is a straight line, then you use one member. If the model one beam using many cube elements, then you have n elements for one beams. What about whole structures? For whole structures, you have many beams, many columns, right? If you have to multiply n by n times, the number of elements in the structures. It makes the calculation much more higher if you're using 3D elements. So finally, go back to the scope of this module, what you are going to learn. At the beginning, today, we start to discuss simplest method. Simplest method is also called matrix method, matrix approach. You can use matrix approach to solve static problem. Find out the moment diagram, find out the diffractions, find out the other thing else. In this module, we will discuss 3 major elements: truss, beam, and frame. Suppose you need to know how to find out the moment diagram and how to find out the diffraction of a frame structures after studying the first chapter. Also some common problem that I asked students in the past. Not that complex, but similar things. And then at the middle of this semester, we move our contents to structural dynamics. Dynamics means something that can move. Say, for example, the loading. The loading is not a constant. A loading can be a time-varying function. A force applied right here at the second story. In the past, you treat this force as a constant, right? But in structural dynamics, the force values can change with time. At the beginning, 0, and then as time goes on, the force can be positive, can be negative, and positive again. The value of force can change. One classical example is earthquake. When earthquake attacks structures, the force magnitude change with time. Or even wind. Wind is theoretically wind can be a dynamic loading. But for design problems, we normally treat wind as a static force, and then multiplied by some amplification factors. And then under this dynamic loading, the structure diffraction is a constant? No, right? If the force changes with time, then diffraction also changes with time. So the diffraction is a function of time, time varying function. At different time instant, you will get different displacement, diffractions. In chapter 2, we will discuss how to find out the response of simple structures under dynamic loadings. We will consider different forms of dynamic loadings. Sinusoidal force, periodic loadings, or arbitrary loadings, these kind of things. The last part we learned something so-called plastic theory. Plastic means yielding. In the previous chapter, we assumed that material remain linear elastic. What is the meaning of linear elastic? Linear elastic. Normally, you can describe this behavior using the force displacement. Displacement. You can display the relationship using force displacement. Linear elastic, actually, you have seen this assumption many times, linear elastic materials. But actually, this term means two things. Linear means the force displacement relationship is a straight line. Linear, right? Linear means straight line. What is the meaning of elastic? Elastic means when you unknow the structures, it will back to the initial point. This means elastic. Okay, you can go back to the undeformed positions without any residual displacement. Elastic. Then what is inelastic? After yielding, okay, maybe here up to this point. When you unknow the structure at this point after yielding, it cannot go back to the initial position. It will go back probably here. Then you can see residual displacement. So this is so-called inelastic. You cannot go back to the undeformed positions. So when you see this term linear elastic, actually it means a lot of things, not just two words. Okay. What about here? Plastic theory means we need to focus on something after yielding. Post means after. We need to know the behavior after yielding. Particularly for a member under bending, a beam. A beam, I think in mechanics of materials, you have learned the stress distribution, linear for beam, right? When the beam under bending, we expect that the stress distribution is linear if the things remain linear elastic. What happened about the stress distribution after yielding? This is something that we would like to discuss in this chapter, chapter 3, plastic theory, post-yield behavior. Then you will probably see a term called plastic hinge. I will explain what is so-called plastic hinge later in chapter 3, don't worry. Now, by the way, this picture is generated using ZAP 2000. ZAP 2000 is a very general software which can help you to handle static, dynamic, and also yielding behavior. We will answer you this question in chapter 3, yielding. These are all the things that we're going to cover in this module. I hope this 3 slides give you some prelim idea what you will learn in Sylva's method, dynamics, and plastic theory. So maybe we can take a 5-minute break. Normally, I give students a break after around 1 hour discussion. Okay, let's have a 5-minute break. Okay, any questions so far?